Hi, my name is Nadia Sidorova. I work at the Department of Mathematics at UCL, and I do research in probability. Probability is a fascinating area full of amazing things. Today, I'm going to show you one of them, and I very much hope you will be surprised by what you see. So, suppose you are sitting at home with your family, you have just finished lunch, and have to make an important decision. Who will be doing the dishes? And let's suppose the choice is between you and your brother. How do you decide? Of course, you can just toss a coin, but this method has a clear disadvantage. It's just too fast. It will throw one of you into the misery too soon. So instead, you get a die, a fair die, and you decide to play the following game. So you roll this die, and each of you picks a particular combination of 3 numbers, which you would like to occur in a row. So you are waiting for the combination 4, 5, 6 to occur in a row, and your brother is a bit more adventurous, so he decides to wait for the combination 6, 6, 6 to occur in a row. So you passionately play this game for a few minutes, because the stake is clearly quite high. And after a while, the die rolls 4, 5, 6 consecutively, which means you have won. Your brother, naturally disappointed, retires to the kitchen, but you don't feel bad about it because the game was clearly fair, right? So every number on a die had an equal chance to occur. However, you're still excited about the game, and having lost your brother as a game partner, you have no other option but to play against the computer. So you write a computer code. I have written one for you. Let me share it with you. So like this one. This code generates random integers between 1 and 6 and stops whenever one of the combinations 4, 5, 6 or 6, 6, 6 first occurs. And it reports you win or you lose accordingly. So you run it for several times and you start getting a strange feeling that perhaps you win a bit more often than you lose. Surprised by that, you change your script a little bit. Now it runs for a million of times and it computes the frequency of stopping at 4, 5, 6 or 6, 6, 6, which you would expect to be 50-50, right? And the shocking answer is that it doesn't seem to be 50-50, but rather you, with the combination 4, 5, 6, win in 55% of the cases. So how come the game, which seemed perfectly fair, turned out to be unfair at the end? So before trying to answer this question, let's look at a much easier question. So suppose we simply roll a die 4 times. And we want to know what the chances are that we see the pattern 4, 5, 6 or the pattern 6, 6, 6 there. So that's simply counting. We count the total number of outcomes, which is 6 to the power 4, because we have 4 attempts, and at each attempt, we can get any of the 6 numbers. And then how many of those outcomes would be successful for 4, 5, 6 and for 6, 6, 6? So for 4, 5, 6, we either must have it in the beginning of the combination, followed by any of the other digits, which gives us 6 options, or it must appear at the end, preceded by any other digit, which is another 6 options. So overall, 12 outcomes are successful for the combination 4, 5, 6. For 6, 6, 6, it's similar. We either want it to appear in the beginning or at the end, but this only gives 11 outcomes, as we cannot count the combination consisting of 4 6s twice. So this observation suggests that the patterns 4, 5, 6 and 6, 6, 6 behave somewhat differently, and in particular that perhaps 666 occurs a bit less frequently than 456. Can we quantify it? Can we say how long do we need for each to wait for each combination to occur? So again, we just add a few lines to our previous script and compute the waiting time of the combination averaged over 1 million of trials. And the answer, so a typical answer that we would get is this. The expected waiting time of 456 seems to be roughly 216, and the expected waiting time of the combination 666 is roughly 258. And now, if you have a good eye for numbers, you will notice that 216 is nothing but 6 cubed, and 258 is the sum of 6 cubed, 6 squared, and 6, which is clearly related to the number of faces a die has. Interesting, right? So can we prove it? If we want to prove it, we need to understand the concept of a martingale. This sounds like a difficult, unfamiliar word, but don't worry about it. The most natural way of thinking about martingales is in terms of fair games. So suppose you play the following fair game. So your initial capital at time 0 is x naught, and then your capital at days 1, 2, 3, and so on will be denoted by x1, x2, x3, and so on. So when would we call such a game fair? Let's think. So suppose it is day n, and we know how the game has evolved until day n, and in particular, we know our current capital xn. What we don't know is how much we'll have tomorrow. So we don't know the value of xn plus 1. So we would call a game fair if the expected value of what we will have tomorrow is no more and no less than what we have today, right? So given all the information at day n, our best prediction for what we will have tomorrow is exactly what we have today. So that's what it means to be fair. Let's look at a couple of very simple examples. The simplest one I could think of is what we call in probability a random walk. In terms of fair games, you start with a tenner, so with 10 pounds, and every day you flip a coin, and if it lands on heads, then you win 1 pound, and otherwise you lose 1 pound. So this is your capital trajectory over a few days. And why we call such a game fair? So if it is day 20 today, and we know how the trajectory behaved until now, so we know all the red bit here, we know we have 8 pounds today on the day 20. What we don't know is what we'll have tomorrow, but we know it will either be 1 more, so 9 pounds, or 1 less, 7 pounds, each with probability 1/2. So on average, we have the same number, 8 pounds for tomorrow. So this is why the game is fair. Of course, you can make it more complicated. In this game, your stake is 1 pound each day, but you can also play a doubling game where, again, you start with 10 pounds and your stake on the in the beginning of the game is 1 pound, but if you lose, like here, you double it. So you bet 2 pounds on the next day, and if you lose again, then you double it to 4. And if you lose again, you double it to 8. But what's good about the doubling game is when you finally win, which here happens on day 3, then you bounce back and you end up 1 pound better off than in the beginning. And then you start over again. As long as you're losing, your stake is doubling, and as soon as you have won, you go back to the original state. So the game seems very attractive, but of course it's quite dangerous because if you lose for a while, then you may go bust. This game is clearly fair because whatever you stake is you are equally likely to go up and down by the same amount, and therefore on average your capital will stay the same. So this is how you can think of fair games and martingales. An important question: can we win in a fair game? Now, of course, we can win a game or two, right? The question is, can we win in the long run? So can we make a living out of playing this game? Unfortunately, it turns out that all fair games, all martingales, have the property that your expected capital at day n is equal to your starting capital. So if you gamble for a fixed number of days, you will neither win nor lose on average. But then we may ask, but what if we gamble until some random time, depending on how the game evolves? So for example, if we play a doubling game, we could say we play until we either first win, which means first reach 11 pounds, or go bust, which unfortunately can't be excluded. So we don't know how many days it will take. It will be a random number of days, but it sounds like a possible gambling strategy, which is based on stopping the game at a random time. Of course, we can only use random times which do not use any information from the future, otherwise no one is going to play with us. For example, we are not allowed to stop the game just before we make our first loss. So that wouldn't be fair, right? So the admissible times, stopping times which we are considering are not using information from the future. And then we go back to the original question, can we win? Can we stop a fair game at a random time in such a way that our expected capital at the time the game is stopped is bigger than our initial capital? Because if so, we are rich. However, there is always a however. There is a theorem called optional sampling theorem, which ruins our dreams. It says that even if we stop a fair game at a reasonably good random time, then our expected capital will be the same as our initial capital. So we cannot win in a fair game in the long run. So let's go back to the original question about 456 and 666. How can martingales help us solve this problem? So we are going to construct a fair game for each combination. Our fair game will be based on throwing a die on each day. And let's do it first for the combination 456. So we will have not just one player, but many players. At each day, a new gambler will arrive on the scene, and each gambler will be playing for at most 3 days. Namely, the one who arrives on day N will be playing on day N, then perhaps next day, and perhaps the day after. And then they will quit the game. So how are they going to gamble? So on their first day, when they arrive on day N, they bet £1 on the outcome, which is the first in our combination, so on 4. So if the die rolls 4, they win £6. I mean, it must be £6 to make the game fair. And otherwise they lose and quit the game. So if they're still there next day, then they bet all their newly acquired capital, £6, and they bet it on the second number in our combination on 5. If the die rolls 5, they win £6², again to make the game fair. Otherwise, they lose everything and quit. And if they continue for another day, very similarly, they bet 6 squared pounds. And if the die rolls 6, then they will 6 cube, otherwise they lose. And now after 3 days, they quit the game anyway. So this is how the game looks like for the gambler arriving on day N. Now, what we learned from the previous slides is that since this game is fair, at any time, the expected total winning by all gamblers must be equal to the expected total investment into the game by all gamblers, right? So now I want to stop this game at the very specific time, namely at the time when the combination 4, 5, 6 first occurs. I denote this time by T, 4, 5, 6. Now I want to compute the expected total winning and the expected total investment at that time. So let's start with the investment because it's easier. So let's see what is the total investment on day 1. There is just one player. It came with £1. So the total investment is £1. On day 2, we have 2 gamblers. Each came with £1. So the total investment is £2. So at any time, the total investment is equal to the number of days the game has been running. So since our time is T456, it means the expected total investment will be the expected value of this time. And by the way, this is what we want to compute, right? So we want to compute how long we have to wait until we see the combination 4, 5, 6 for the first time. So that's exactly this quantity here. On the other hand, what is the expected total winning at that time? So you see, I have written a sum here. This sum corresponds to summing over all gamblers, right? So you see, something special happens for the last 3 of them. But let's look at the first ones first. So what happens to the first gambler, the one who arrived on day 1? We know that for each gambler, when the game is over, they are sitting there either with 0 or with 6 cube pounds. And 6 cube is possible if and only if during their 3 days of gambling, they observe 4, 5, 6 to occur, which is clearly not the case for the first guy, right? Because the combination 4, 5, 6 has occurred during the last 3 days. So this means we know for sure the first guy has lost and his winning is 0 or her. And the same argument works for all guys except the last 3, because for all of them the game is over and they haven't experienced the combination 4, 5, 6. So it's 0 for all of them. Now let's look at the second class guy. He or she is a lucky one because it's during their time the combination 4, 5, 6 occurred first. This means they pocketed 6 cube pounds. Very nice. Now, how about the second last guy? Their game has not finished yet. They are into the second day of gambling, and they wanted to see the combination 4, 5 during the first 2 days. But what they saw was 5, 6, right? Because we know the last 3 digits, the last 3 outcomes were 4, 5, 6. So not what they wanted to see at all, which means they lost. And similarly for the last guy, he or she wanted to see the number 4 on their first day, but we know this number on the die was 6. So this gambler has lost as well. So since we know that the total investment is equal to the total winning, we know that the expected waiting time for the combination 4, 5, 6 is simply 6 cube coming from the third last gambler. Very nice. Now, what's different for 666? I will construct a slightly different game, but it will be very, very similar. It's just that all gamblers use now the number 666 on their 3 days of gamblings. So each of them wants 6 on the first day, 6 on the second day, and 6 on the last day. Now I want to stop this game at the time, which I denote by T666, when this combination 666 first occurs. It is still true that the expected total winning is equal to the expected total investment. It is still true that the expected total investment is simply the average waiting time for 666. What is going to change is the expected total winning. Let's look at the last line here. Actually, nothing is going to change for the first guys. For them, the game is over, and 666 did not occur during their time of play. Nothing is going to change for the lucky gambler, who's the third last. They have won. They have got 6 cube. But the difference will come from the last 2 gamblers. The second last guy, during their 2 days of gambling, has experienced the combination 6-6, which is exactly what they wanted to see, right? Which means they are still in the game. They're sitting there with 6 squared pounds. And similar for the last one, we know the last 3 outcomes were 6-6-6. In particular, the first outcome for this last guy was 6, but they are happy with this, right? That's what they want to see on the first day. So which means they have not lost. They are sitting there with 6 pounds. And this means the formula for the average waiting time for having the combination 6-6-6 is a bit bigger than in the previous case. It's 6 cubed plus 6 squared plus 6. And we have now proved it. So now I have a couple of questions to you. The first one is, what do you think is the average waiting time for the combination 6-4-6? You can use exactly the same logic as we did for the combinations 4-5-6 and 6-6-6 to answer this question. And the second question is, can you find a combination for which the expected waiting time would be 6 cubed plus 6 squared? Okay, so this is the end of the video. I hope you enjoyed it. If you have any questions, please get in touch. And thanks for watching.